Okay, so today we'll talk about the difference between single crystalline material and polycrystalline material. Okay, when we can call a material single crystalline material? It's a very good question. And this is not only a very good question, it's a very important question because many of the technological applications, okay, it needs single crystalline material, okay? Many of the electronic microcircuits that you have around you, okay, depends on single crystal material, okay, of silicon more specifically. So what is the single crystal? What does that mean when you say single crystalline material? It means that the arrangement of atoms is perfect. So the periodic arrangement of atoms in all the directions are not interrupted by any impurities or defects. Okay? So the unit cell are interlocked to interlock in a way that they have the same orientation. It's like you're taking a unit cell and you do copy paste into the top, copy paste to the right, copy paste to the left, copy paste in all the directions in order to build the material without any interruption. And this is called single crystalline material, okay, a single crystal, okay? Now, single crystalline material can exist naturally. You can find it. But also we can produce this kind of material, but that typically or normally it needs a careful or specific type of environment. So usually they grow what's called single crystalline material in what's called clean room, where you try to prevent the existence of impurities that might interrupt the growth of the single crystalline material. Okay. The second type of crystalline material is called polycrystalline material. Okay, polycrystalline material. That means a material that's composed of number of single crystalline material. Okay. Now, why this is important? Well, because when we deal with single crystalline material, we can call this kind of material, they are anisotropic. Why? Because the properties in this kind of material depend on the direction in which the measurements are taken. However, when you go to polycrystalline material, I'm going to talk more about what's happening during the growth of polycrystalline material, okay, in a minute. But I want to tell you why this is important to differentiate and to distinguish between single crystalline material and polycrystalline material. In polycrystalline material, okay, the properties are independent of the direction of measurement. Okay. And this is why the polycrystalline material is called isotropic. So they are isotropic. So the difference between anisotropy and isotropic is the dependence of the properties on the directions. Okay, so an isotropic material, that means it depends on the direction. Isotropic material, they does not depend on the direction. Now let's see if we have an aluminum, a single crystalline material. Okay, for example, we're dealing with aluminum. Okay, for let's take the copper. You see that the modulus of elasticity, which is something we're going to talk about a lot when we go to the mechanical properties later. So the modulus of elasticity is measuring how much the material can resist a permanent deformation, okay? Something that we're going to talk about later. So modulus of elasticity, which is a property of material, okay, is different in 100 compared to other directions, okay? You can see that the value is different. Okay? And also here for the aluminum, okay, you see the values is different, okay? So this value is different than this, is different than that, okay? And that means the properties depends on the direction in which it's measured. It's called anisotropy. So the material where the property is different according to the directions is called anisotropic material. Okay. Now for polycrystalline material, we call it isotropic because the properties will not depend on direction, and the reason behind that because the directions of each single crystal, okay, because the property will be averaged out when you look at each single crystal. What are you talking about? What do you mean different single crystal? What do you mean orientation of each single crystal? Okay, I think things maybe is like a buzzy word, huh? Okay, don't worry, okay? Now let me make things much clearer. If you watch what's happening during the solidification process of a material, okay, you start with a liquid. You start with a liquid, and you want to solidify that liquid. You transfer it from liquid phase to solid phase. So the gray color here is representing the liquid phase, and then the blue one is representing the crystal that start to form. Okay. Now, what you notice here? Well, you notice that the new crystals start to form as you do the solidification. Okay. So start to form. So atoms come together to form this square grid over here. Okay, here more atoms coming to form. Crystals that have two square grid. Okay, here also you have crystals or nuclei start to come together in order to transfer for to nuclei to initiate the nucleation process and then the growth. Okay, you notice that the direction. So all these here they have the same orientation, the same crystallographic orientation. Okay, but the one over here it's different, right? It has different orientation compared to this one. Right now, this one, and those all different new crystals, they continue to grow. So they will take the atom, so it will be addition of atoms from the liquid to this crystal in order to allow this crystal to grow. So this crystal over here, they start to grow, and the one over here will start to grow. And then what's going to happen, they will grow and grow and grow until they hit each other. Now you notice that the crystallographic orientation here is different than crystallographic orientation here. Although they are the same within the this region, it's different than the other regions. Okay, so we can call this region here a single crystal material, because in single crystalline material, this should grow through and extend it throughout the whole material, throughout the sample without any interruption, right? But this is not happening when you have polycrystalline material. So in polycrystalline material, you see that we have here, they are growing in a certain direction that's different than here, that's different than here, that's different than here. So we can call this single crystalline material, single crystalline material, single crystalline material, single crystalline material, right? And this is why we call the whole material a polycrystalline material, okay? Now, if let's say, the elastic modulus, the one that I just showed you in the previous slide in a table, okay, in a certain direction here, it equals a certain value, okay? That value, that direction will be different here, okay? Right? Will be different here, will be different here. So the directions are, the orientation of those directions, will be different, right? So that means when you look at the property of a polycrystalline material, it will be an averaged out, measurement of all, by considering all these different single crystals within the polycrystalline material. Okay. Now we can call this a grain, and we can call this a grain. So we can call it single crystal. We can call it the grain and the grain and the grain. And you notice that between them there is an atomic mismatch between the atoms. There is a gap between them, right? They cannot go further. So they grow, and then they hit each other, and they cannot grow further. And the gap between them is called grain boundary. Okay, grain boundary. So you have grains, and then between them you have the grain boundaries. Okay, great. So that means now in polycrystalline material, we have single crystal, single crystal, single crystal. Okay, so we have polycrystalline material, and the property will be the average of all the single crystals that you have here. Okay, this is called polycrystalline material. This is why in polycrystalline material, the property does not depend on the direction, because at the end it will be the average, because the 110 here, the 110 here is different than the 110 here. If we'd say, for example, if we say a certain direction, let's say 110 is the best direction, or the direction that's going to give you the highest value for a certain property. For example, okay, again, if we say a certain direction, it has the highest value for a certain property. And let's call that direction 100, okay? So 100 here, direction, is different than 100 here, right? So that means we cannot say that there is a single, we cannot say that this is the 100 of the polycrystalline material, because at the end it will be the average of the grains. Okay, I hope it's clear by now. And what I want to say, just an additional note, that sometimes the polycrystalline material, sometimes there is a preferential orientation, okay, for a certain property. For example, for a certain property, you might find that polycrystalline material might have some preferential orientation. I mean, there's a certain thing that's happening for 100 type, for example, 001 type, okay? For example, we call this texture. So when a polycrystalline material has a texture, that means there is a certain preferred orientation where a certain property is happening. But in general, we can say that the property is being averaged out, okay? It's being averaged out, okay? By this, by knowing this, we can differentiate now between polycrystalline material and single crystalline material. Okay, so this is the end of chapter 3 and 4. I hope by now you know more about what's called crystal structure. Remember at the beginning, we say that in this course, we're going to start from how two atoms interact with each other, what kind of bonding can exist between two atoms. And then we say we're going to see what's going to happen if we have millions of atoms coming together, right, to build the material. And that's, chapter 3 and 4 try to give you, another lens to see what's happening inside the material, how the atoms are correlated to each other, how they can be, what are the possible way of arrangement or positioning, or inside that kind of material, and also how we can point out or identify planes or directions within the crystal system, because that at the end will help us to maybe distinguish between their properties. We can group them in family. So we can say for a certain family, we're expecting the property to be in a certain way. Well, it's going to be higher or lower, or be an average, or maybe the property of all these directions does not depend on, this direction has nothing to, it does not play a major role, or the directions of a material does not play a major role for a certain property. But and then we end this by saying that we have single crystalline material, we have polycrystalline material, and most of the material around you, they are polycrystalline material. They are polycrystalline material because in polycrystalline material, during the certification process, you might have impurities that's coming from the mold during the certification, so that will interrupt the growth of the crystal. Again, here, if you look at here, why you have here more crystal than here? Because there's something that is triggering, or the driving force for the crystal growth here is larger than the driving force of the crystal over here, right? So this is why, because the driving forces is different, okay, during the certification, you will have different, the crystals start to form different regions with different, driving force, different speed. This is why at the end, when they hit each other, they will have different orientation. And this was maybe the polycrystallinity. If we can control the environment, then we can make, this crystal over here to extend throughout the material. So the whole material will have, something exactly similar to this. We're going to take this. We're gonna take, this line gonna continue here, and this line gonna continue here, and this line gonna continue. So all the the square grids will come, next to each other without any interruption. This is called single crystalline. But here, because polycrystalline material, no, there will be some interruption. There will be some grain boundary exists between them, and also each crystal, each grain has different orientation. Okay, I'll stop here.